all the different gauges, inputs of data from the turbo pump. It will log everything in a big data file. So it generates a D log, which is the data log, and an E log, which is the event log. If we hit this button, it will change the names of the log files to be the same as the run ID. So we just generally use that all of the time. Any comments here? So you put like repeat of failed bond or attempt 3 or something like that. You can put comments in there if you choose. Vacuum pump. There's a few parameters here that you won't need to change, but they're there anyway. So we leave the pump with automatic venting. So what happens is when the pump spools down to 60% of its maximum speed, the pump will then vent itself in a controlled manner. So we supply it with half a bar of nitrogen through a small tube, and there's a controlled venting valve that will inject nitrogen into the turbo chamber and slow down the rotor. It's kind of an air brake, and the pump controls itself doing that using automatic venting. Alternatively, we can force it to turn the venting on. I recommend not doing that. And if for some reason you don't want the pump to vent, you can set it to don't vent. I would also recommend not doing that because it takes about 15 minutes for the pump to stop without any venting, whereas it takes about 5 minutes to stop with venting. You won't be able to start a second run. You won't be able to open the isolation valve until the pump has stopped spinning. So the venting kind of helps to speed things up there. Then you've got some parameters for venting speed and vent time. Don't need to change those. This is fairly important here. We've got a log, running hours since the last oil change in the pump, and a number of days since the oil was last changed. I'll set those back to 0 before I leave, because we've had minimal usage of the pump during the sort of testing and setup, so it still essentially is new. The frequency of the oil changing is every 2 years, or if prompted by the pump. So if you've been using the machine a lot, it's got a lot of hours logged on the turbo pump, it may request before 2 years are up that you change the oil. If it hasn't requested it, change it every 2 years, whichever comes first. We've got some parameters here for logging intervals. So at the moment, the software will create a data point in the data log file every 2 seconds, or if any parameter varies by more than 100% from its last logged point. You can change this to say 600 seconds, so every 10 minutes if you're doing like an overnight run. The idea of that is that it then prevents the log file from becoming excessively large. Oh no, I'm fine.
I'm going to put this on tripod.
Okay.
Yeah, because my hand is numb.
Okay. The last 2 parameters, wafer thicknesses of the upper and lower wafer. These are important. Do you know what thickness your wafers are?
Yes, 1 and 500 or 500 and 500. 1 millimeter 500 micron or 500 and 500.
So 1.5 or 500 micron. Okay.
But is there like a maximum thickness?
No, not really. The manipulator can separate by 30 millimeters, so if your stack is less than 30 millimeters, it will fit. Right. So yeah, we can input the upper and lower wafer thicknesses here. It's important to do that before you start the run because the software uses those parameters to calculate the wafer separation. So it will use a 0 point reading that I'll talk you through later, the actual reading from this encoder, and the thicknesses of the wafers that you tell it here to calculate the theoretical separation of your wafers. It's important that that's accurate because when you do alignment, you want the separation to be only, say, 200 microns, 100 microns, and you don't want to bring the wafers into contact before you intend to. So it's important to set these to be the correct thickness. Okay, so when everything on this screen is set up, you can click OK. And we're onto the main screen. Before we can select anything, it's all greyed out there. We have to click Start. So we start the process. Now we have control of the machine. So I'm going to talk you through this side of the screen first, and I'll talk you through this toolbar later. So, firstly we have a timer. This doesn't actually do anything. It won't force anything to start or stop, but it's just a useful tool if you want to time 5 minutes of bonding time, or 10 minutes of plasma activation, or time how long it takes to heat your wafers up, for example. You can use this timer. You can set a time, so say you want to do for 5 minutes in there, you can set 5. When you click Start, it will then count down from 5 minutes, or maybe it counts up to 5 minutes, I don't know. After 5 minutes have elapsed, this will start flashing red. It won't interrupt anything, it won't do anything, but it will just start flashing red to let you know that 5 minutes have elapsed. If you set this to 0, so say you want to, instead of you want to do something for 5 minutes, you want to time how long something takes, start it at 0, then the clock will just count up and it will keep counting up, so you can keep a log of how long things take. Valves, there are 3 valves that we can control. The isolation valve, that's what separates the chamber from the pump. The idea of that is that you can close the isolation valve and then you can vent the chamber while the pump is still spinning. So otherwise you'd have to wait for the pump to stop before you could vent the chamber. So we don't want to vent the pump while it's spinning because that can damage the pump. So it's there to protect the pump and also save you time, because you don't want to be waiting for the pump to stop because it takes a while. So you can shut the valve, vent the chamber, then take your wafers out while the pump controls itself. So that's opening it. There's an indicator that will show you when it's open. The software uses that to then grey out other things. So for example, in this situation, it won't allow you to open the nitrogen cooling valve while the gate valve is open, because it doesn't want you to force a load of air into the pump. So the software uses this indicator to protect the pump. Nitrogen valve, I showed earlier, it's the cooling ring inside the chamber. So here we can hear the exhaust coming out of the exhaust valve. We can control the nitrogen valve. We can open and close it whenever we like, provided the isolation valve is closed. When we open that, the software will then take control of the exhaust valve and open it at 1100 millibar pressure, or whatever pressure you set in the configuration program, as I taught you through earlier. Currently we can use the exhaust, we can open and close the exhaust valve manually as well. So once the software's finished controlling it, it will allow us to control it if we so need. So say you're doing your overpressure bonding, you've got 2 bar, you've got an excess of gas in there. You don't want to open the nitrogen valve because you've already got overpressure in there, so you'd open the exhaust valve to vent the excess pressure out into the room. That's how you vent back down to atmospheric pressure after doing an overpressure bond. Pump is a simple on and off. You tell it to turn on, you tell it to turn off. The pump is quite intelligent. It has its own control unit, so it will control itself. It even has a battery in it, so if there's a power failure, the pump will be able to control itself to a safe point, and then it will shut down. So it's there to protect itself. It's quite an expensive piece of kit, so it's good that it does that. You've got 3 options here. We can view the rotor speed of the pump. That has a maximum speed of 1500 Hertz. We can observe the current draw. So what we expect to see is when the pump is ramping up, when it's accelerating, we'd expect to see that up to a maximum of about 3.8 amps. When it's under vacuum and it's just in a steady state, we expect to see less than 1 amp, ideally around about 0.6 to 0.8 of an amp. If under vacuum you observe a higher current, higher than 1 amp, it's potentially indicative that there's a leak or that the backing line performance is impaired in some way, maybe a kink in the line or the pump not functioning properly. So that's kind of an indication that you maybe have a problem if the drawn current is high. Lastly, you can see any error codes that are generated. So the pump will, if the pump has a problem, it will throw an error code. It will be a meaningless string of numbers and letters, but you can look at the manual to cross-reference what that error code means and report to us or try and fix it. Over here we have control of the vacuum system. So this is where we're going to control pressure from. At the moment, I've selected in the configuration program to use the narrow range accurate CMR gauge. So the value that we can input into this box is restricted to the range at which that gauge is capable of controlling. So if you try to request a value outside of that range, it will not allow it. It will snap back to the lowest pressure is 2.5 to the -1. And if I try and say put 2 bar, actually if I put 2 bar, that will work. It will also allow you to do overpressure bonding basically. Process gas in this case is nitrogen. The option is there for machines that have multiple process gas lines. You can change that if you so wish. There's a little list of things there. So say you've plumbed argon into the system, you can change that over to run argon. I think if you do change that, it will then force you to run a purge cycle. So the purge, you just flick on and off there. When you flick that on, it will pump the chamber out to 1 times 10 to the -4 millibar, and then it will backfill with your process gas. So I recommend doing that. If you attach any of your other gases to the process gas line, select the gas as appropriate from this list. And if it's not there on the list and you can't select it, just run the purge sequence anyway. Then we've got here a digital display that shows the current chamber pressure, and as well we've got the needle meter, like a graphical display of the chamber pressure on a logarithmic scale. When you can see here there's a little grey arrow. When you activate pressure control, that grey arrow turns blue and it will move to whatever position you've requested. So what you're going to hope to see is the red needle and the blue needle line up with each other when the pressure's being controlled and is stable at whatever value you've requested. Heaters, simple to operate. We simply input the desired temperature in the boxes there, and when you want to turn them off, hit the off button. All that does is then set the temperature to 0, so the heaters will cut out. We've also got option for controlled heating and slow cooling. So controlled heating, if we go into that, we can request target temperatures, and we can also request a heating, like a ramp up rate. So if for any reason you want to heat it slowly or in a controlled fashion, you can do it from there, although I've never known anyone actually use that. But the option is there if you need. Similarly with slow cooling, you can set a cooling rate, and what this will do is use the nitrogen cooling but also use the heaters to balance so that it will achieve a controlled cooling rate. Again, I've never known anyone want to cool it down slower. It's slow enough as it is. They want it to cool down as quickly as possible so you can get on with the next run. But there we go. Platen force. We have a reading here of the current platen force. I mentioned earlier on that you can get negative figures here. That's to do with the mismatch of the force compensators in the Z bellows combined with the weight of the manipulator, combined with the 0 point. So there's a series of fairly complex interactions that essentially result in it being a negative force. The idea is you'll zero the force at the level, like just before you make contact with the wafers. You zero the force off there. Whatever it's displaying gets stripped away. It gets like subtracted out of the calculation, and then if you ask for 5 kilonewtons of force, it will give you 5 kilonewtons. Similarly with separation, it's just currently displayed there. We can zero that using the bonding voltage. We can apply a small voltage to the platens, bring them into contact, see when it shorts out, then we can set that as a 0 position, and from there the software knows the point where the wafers come into contact, and from there it can calculate your separation. So I'll talk you through that later, zeroing. You also have the option here to set a force or set a separation, and then control the force and control the separation. So if I want to separate the platen to say 7 millimeters, I can request 7 millimeters in there, control separation. And the software then takes over the motor and delivers me 7 millimeters of separation. Similarly, if I want to put force, I can request a force in there, hit controlling force. Again, the software just takes control of the motor and applies whatever force you've requested. Then you've also got manual control where you can just move the Z drive up and down using the keyboard. So controlling the manipulator is accomplished via the keyboard. Up moves the Z drive up, down moves it down obviously, left and right moves the theta anti-clockwise and clockwise. And then to move in X and Y, it's space bar plus up and down. That will move the Y axis positive and negative. Space bar plus left and right moves the X axis in positive and negative directions. We'll see that later in action when we do some alignment work. RAD, this is the plasma system. So we can request a voltage and a current here. As I mentioned earlier when we went through the configuration program, the default values are set to 500 volts, 100 milliamps. So that's what it's automatically put in there. Those values work, they're fine. But if you want to have a less intense plasma, you can reduce the current or reduce the voltage accordingly. You've got a toggle switch to turn the plasma on and off. We recommend operating the plasma at 1 millibar. Much lower than 1 millibar, it will work down to about 0.5 of a millibar. I think it works. Pressures below 0.5 of a millibar, there's not enough gas in the chamber for it to ignite the plasma. So 1 millibar gives a nice stable plasma. And then here we have a monitored voltage and current. So these are our requested values, and these are what the power supply is actually delivering. It'll be current limited to start with, so usually what will happen is you'll turn the plasma on and you'll see a voltage of approximately 420 volts. That's what's needed to deliver a current of 100 milliamps. As the ring starts to heat up when it's in operation, the voltage will increase, and eventually if you leave it running for a very long time, 20 minutes, half an hour, the voltage will top out at 500 volts. It can't go any higher than that. That's the maximum the power supply can deliver, and then the current will start to exponentially decay. That's kind of normal. Generally, for doing a direct bond, we recommend about 10 minutes of plasma activation, so you should never hit the voltage limit with a 10-minute run. Lastly, down at the bottom here, we've got the bonding voltage, high voltage. So this we can go to a maximum of 2.5 kilovolts. I don't know any bonding process that requires 2.5 kilovolts, but the capacity is there. Generally speaking, for a 4-inch wafer, 800 volts is sufficient. So in these two boxes, we have target voltage and the current limit. These are the values that we can request. So we request 800 volts, 4 milliamps. In these two boxes, there's a monitor that shows what the power supply is actually delivering. There's a separate timer down here when you switch the bonding voltage on, this timer automatically activates so that you can time how long you've been applying the voltage for. And there's also a little box that calculates charge transfer. So if you're seeing charge being transferred, you can be fairly confident that the bond is forming, that it's working. For a 4-inch wafer, we expect to see somewhere around 2000 millicoulombs plus minus 500 or so in there. So if you only get 1 or 2 millicoulombs of charge transfer, you can be pretty confident the bond has failed. If you see some charge transfer, then the bond is probably working. This graph plots voltage on the left axis, current on the right axis, and they're both scalable. So say we're using 800 volts, you can maybe put 900 in there, and it will just rescale the graph accordingly. Maximum current that the bonding voltage power supply can deliver is 40 milliamps. Typically we're going to use about 4 milliamps for bonding a 4-inch wafer. Okay, so that's basically all of the controls of all the systems. Then we've got these parameters down the side. So view cameras. This is what we're going to use for doing alignment. So here we have the view from the left camera, the view from the right camera. We have control of the illumination via these two toggle switches, so visible illumination or infrared illumination. At the moment I've got a glass wafer on the upper platen and a silicon wafer on the lower platen, so I can use visible light to do that, to look at that. We've got these sliders for controlling the gain and the shutter to improve the contrast. Then we can try and move this microscope to focus on something. So there we have some rubbish on the wafer. And there we have some alignment marks. So we can move the cameras around